anyway. That's why this meeting.
Great. Okay, that's it. I'm glad you're able to have it. Yes,
right.
We're streaming now.
Okay, we're streaming now, and Junaid, the repertoire is on board, right?
So, Sushilji.
Yes.
Hi, this is Junaid.
Yeah, hi.
Hi. So today's reporter is Dr. Saurabh Ghosh.
Oh, Saurabh. Nice,
yeah.
nice
yes,
to see Saurabh.
Anyway, nice to meet Dr. Yaron and Dr. Mehul. Hi.
Nice to meet you too.
Hello, Professor Mojumdar. How are you?
Very good, Saurabh. Nice to hear from you after a while. How are things?
Yeah, it's okay.
Cool, cool. Well, now that you are here, I'm going to switch off my mic and video and let you take over.
Yeah. Okay, so should we start?
Yeah.
Yeah. Okay. Very good evening to all of you, and a very welcome to the session 2D, Complex and Meta Nanophotonics, Classical to Quantum. So in this session, we have one invited talk will be given by Dr. Mehul Malik, and we have three contributed talks. So the invited talk will be of 30 minutes, 25 minutes of presentation, and 5 minutes followed by 5 minutes of discussion. And the contributed talk will be total 10 minutes, 8 minutes of talk, and 2 minutes of discussions. And first, I want to start the session by introducing the chair of the session to the audience. So this session will be chaired by Dr. Yorin Bomberg from the Hebrew University of Jerusalem, Israel. So Dr. Bomberg is well known in the field of complex photonics, complex photonic systems, and he is from Rira Institute of Physics and is currently heading the complex photonics laboratory. His group studying experimentally how light interacts with complex photonic systems such as scattering media, disordered multimode fibers, aperiodic photonic crystals, and more. Such systems are composed of large number of spiral, spectral, and polarization degrees of freedom, which are strongly coupled to the disorder. His group is, and his research is curiosity-driven research focused on understanding the fascinating physical phenomena that emerge in these systems, which exhibit both the quantum, that is particle-like, and classical, web-like nature of matter. So with that short, brief introduction, I would like to request Dr. Bomberg to please take the session as a chair. Thank you.
Thank you, Sabu, for the kind introduction, and thank you all for joining us for this session 2D. And we're very happy to start this session by our first invited talk by Professor Mehul Malik from the Harriet Watt University from Edinburgh. Mehul has lots of fascinating works on quantum entanglement, quantum imaging, quantum information, and very recently lots of interesting developments in high-dimensional quantum states of light. He has several distinguished awards. He won the EPSRC Early Career Fellow Award. He was a Marie Curie postdoc, and also a very impressive citation in H-index for a young researcher, over H-index of 31 and over 3,600 citations. And today he'll be telling us about unscrambling entanglement. So please, Professor Malik, the floor is yours.
Great, thank you, Yaron. Thanks for that nice introduction. Give me just a second. I'll share my screen. Okay, can you guys see that?
Yes.
Okay, perfect. All right, so let me start by telling you a little bit about my group. So this is work actually done in collaboration with another early career lecturer in Glasgow, Hugo Defienne, who some of you may know. Right, so just a quick introduction to my research group. We are at Harriet Watt University in Edinburgh, which is over here in the north of the United Kingdom. We're a little bit outside the city, and you can see a lot of our recent work at our website, which is bbqlab.org. And we will be, or I essentially will be looking for postdocs and PhDs soon So if you're interested in the work I will be talking about, please do get in touch. We work on a variety of different topics. As Yaron pointed out, we work on high dimensional quantum systems, all the way to sort of quantum information theoretical studies of in quantum information. Today, though, I'll be focusing on a few of these, which is kind of one of the things I really enjoy is trying to bridge two fields that don't necessarily always talk to each other, which is complex photonics and high dimensional quantum systems, which it almost naturally should be talking to each other, but I think it's mainly over developments over the last decade or so that have enabled this conversation to start. Right, so a rough outline of my talk today, I'm going to give you sort of a flavor of a few different things without necessarily getting very deep into individual topics. So first, I will introduce generally the field of quantum tech and where it is today. I'll talk about entanglement and high dimensional quantum states, which we call qubits. Then the second part of my talk is about how do we measure entanglement, or how do we measure it efficiently? And then finally, perhaps something more familiar with the audience today is how do you unscramble this spooky quantum property through a complex scattering medium? Right, so let's begin with just a brief history lesson on what people call the first quantum revolution, which is really the second half of the last century, which describes technologies based on the coherent control of many quantum systems at once, right? These are things that we are familiar with, such as the transistor, the laser, GPS, things we use every day, right? And in medical imaging. So today, what people are calling a second quantum revolution is a revolution based on the control and engineering of individual quantum systems, like photons or atoms, and they rely on uniquely quantum effects such as superposition and entanglement. So some highlights of I guess, achievements in this second revolution include the entanglement from space. So the Chinese satellite, you may have heard, enabled quantum communication and entanglement across 2 ground stations on the Earth, separated by about 1,200 kilometers. Then Google has made huge strides in quantum computing, developing a 70 to 72, I believe, qubit processor. And LIGO in gravitational wave astronomy is getting upgraded with squeezed light, which will, I don't know if you can read the fine print, it says, lead to daily gravitational wave detections, which I feel like is already happening, I'm not sure. But alongside all of these sort of advances, there's also major funding programs, which is perhaps of different interest to academics, is huge funding programs, including one recently launched by India, I believe, and of course this I used to have Trump's picture on this page, but now I have great pleasure in putting across his face. But the US also recently launched a big, massive quantum research program. And so this is just to give you a sense that there's a lot of things happening in quantum technology today. So what is the role of photons in all of this? So photons are really the ideal carriers of quantum information, right? There are many platforms that are in the running for quantum computing, but photons are really the only ones that are efficiently enable you to send quantum information across a channel. And the reasons for these are they're fast, right? They travel at the speed of light. They're cheap, easily available. They don't interact much with the environment, which is a plus and a minus. And they can be efficiently transported through waveguides, right? And above all else, we are building on a massive sort of already existing classical photonics industry and backbone of research, which is essentially the topic of this conference as well, which is nanophotonics. So today, quantum sources of light and ways to detect them are fast-reaching maturity. So we have very bright sources of entangled photons, very high quality sources of single photons, as you already heard today about quantum dots, and very good superconducting detectors, which can detect photons with near unit efficiency, 90, 95%, even 93, I believe is the record. So quantum optical interconnects are seen as links in a global quantum network, in this sort of vision of a global quantum network, which is sort of quantum processors interconnected with quantum optical links. Right. So I thought I would briefly introduce entanglement, since this is not a quantum specific conference. And you may, and I'm going to be using Dirac notation a lot, which is simply just state representation using these ket vectors, right? So you may be familiar with the concept of polarization entanglement, right? Which describes two photons, 1 and 2, that are entangled in their quantum property of polarization, right? And this basically describes a state where if you measure in the horizontal vertical basis, the polarizations of these two photons will be perfectly correlated, right? So if you measure one photon to be vertical, its partner will be vertical. And if you measure one photon to be horizontal, the other photon will also be horizontally polarized. And this is a single photon property, right? Now, what's unique about entanglement is that if you change the basis, measurements in a mutually unbiased basis, I will come to what exactly a mutually unbiased basis is in a second. Measurements in a sort of mutually unbiased basis will also be perfectly correlated. So if you measure in the diagonal anti-diagonal basis, and now if you do some simple math and you write this this state in this dA basis, you will find that indeed this state is perfectly correlated also in this dA basis, as we say, right? So now this is a signature of entanglement. If you take anything away from my talk, I would like you to remember that entanglement is perfect correlations in multiple bases, right? So when you have position and momentum correlations, that is a signature of entanglement. You cannot have a classically correlated state that is perfectly correlated in two conjugate degrees of freedom, such as position and momentum, or in the case of polarization, which is a discrete quantum property, you cannot have perfect correlations in two mutually unbiased bases in a classically correlated state. So we generate entanglement traditionally using nonlinear crystals, where one photon, higher energy photon, is absorbed and two low energy photons are emitted, which are usually entangled in some quantum property. Polarization, you have to play some tricks, but usually they're entangled in position and momentum or time frequency. Broadly speaking, there are some very significant applications of entanglement. One of them is, of course, measurement-based quantum computation and quantum error correction. Another one that is sort of something that I'm working on is device-independent quantum cryptography, where you can have security independent of any of the devices, right? So you could give your encoding device and your measurement device and your channel to Eve, the eavesdropper, and you can still have guaranteed perfect security. So quick introduction about high dimensional quantum systems. So far I've spoken about, qubits, which are the quantum analog of binary encoding, right? So, and this has formed qubits, or polarization qubits specifically, have formed a workhorse for quantum technologies right from the very start. So they've been used for fundamental demonstrations of quantum physics and tests of entanglement. But as we all know, you can encode a lot of information on a photon. You can encode information in the temporal or the spatial degree of a photon. These are just pictures of laser modes. And these are some more complex spatial modes of a photon. In quantum mechanics, we would treat this as a D-level quantum system, or QDIT, where I'm writing them as a coherent superposition of different probability amplitudes, right? Different states, essentially. And you can have entanglement, this property that I described, within these high dimensional degrees of freedom. So you can have perfect correlations in the orbital angular momentum of a photon, which is, again, a transverse spatial property. So if you have one photon carrying LH bar of orbital angular momentum, its entangled partner will always carry minus LH bar of OAM. And the state would be written in this way, where you have equal but opposite amounts of OAM. So why go to high dimensions in quantum mechanics? Well, the obvious answer is that you can encode more information per quantum particle, right? So here I'm showing you a graph where I'm showing you how the field of classical comms has been increasing in data rates and is expected to increase by through the adoption of higher dimensional encoding schemes like wavelength division multiplexing or space division multiplexing. Similarly, you can make a graph for quantum comms where huge jumps in rates have been achieved by adopting time frequency modulation, or one can imagine achieving those same kind of orders of magnitude improvements by adopting space and momentum encoding. The other slightly more subtle advantage that is becoming more and more apparent in the work that we are doing here actually is that encoding information in high dimensions in quantum information gives you a significant noise advantage. You can tolerate a lot more noise before you lose certain quantum properties such as entanglement before with high dimensional states as opposed to qubit states. But of course, everything is not peachy, as they say. There are significant challenges in adopting high dimensional quantum states of light. We have to learn to transport them efficiently, manipulate them, perform operations on them, and measure them efficiently. And these are all significant challenges, two of which I will talk about in the next few slides. Right, so that brings me to the measurement of entanglement, which is not a trivial thing. It's rather hard, mainly because their high dimensional quantum states become very large, and there's a lot of things to measure. So a little aside into theory. So the entanglement dimensionality, which is the size of an entangled state, is routinely measured or quantified by a property called the Schmidt rank. And the Schmidt rank is the minimum number of levels needed to represent a state and its correlations in any local basis. You are probably familiar with the Schmidt decomposition. So this is the entangled state written in its Schmidt decomposition, and where the number of Schmidt coefficients or the number of non-zero coefficients in this Schmidt decomposition essentially is the Schmidt rank. Okay, and formally, if you have a density matrix describing a quantum state, it is the rank of the partial trace of this state, right? That's the more formal mathematical definition, but it's also valid for mixed states. Okay, so usually a quantum state can be measured completely through the process of full state tomography. So this was an experiment 10 years ago where they measured an 8 by 8 dimensional quantum state through full state tomography, where they measured everything. And it required many measurements, right? So it required 8 squared times 8 plus 1, 9 squared measurements. And it took very long, and it required a lot of post-processing. And I believe using pretty state-of-the-art equipment at the time, this took them about 4 days, right? People have done, including myself and some colleagues, have developed other sorts of witnesses for entanglement where you don't need to make as many measurements. So we got away with order D cubed measurements. But this was also quite time consuming. I call this a 2D fidelity witness because we are looking in 2-dimensional subspaces of these high dimensional states. So you have to make many, many measurements there as well. So what was really missing in this field was an assumption-free, sort of efficient way of measuring entanglement. And to do this, we used this concept of mutually unbiased bases, which I've already talked about briefly, where you're familiar with MUBs in polarization. So this is the horizontal vertical basis, let's say. So the first MUB for polarization is the dA basis, which is composed of superpositions of horizontal and vertical. And another MUB is the left and right circular basis, right? So high dimensional states can also have MUBs, mutually unbiased bases. Here I'm showing you different MUBs of an OAM's basis of 11 modes. And in general, for prime dimensions, you have D+1 MUBs. This is a formula for MUBs that was proposed by Bill Wooters and Brian Fields in '89, but there are many different constructions you can have for mutually unbiased bases in high dimensions, right? In fact, you can have many constructions even in 3 dimensions, or 2 dimensions, sorry. Right, so what I wanted to basically show here is that these MUBs have interesting structures. They produce pretty pictures, but they're also quite useful for measuring entanglement efficiently. So without, again, going into a lot of details of how this works, we can use correlations in two mobs of a high dimensional state to lower bound the fidelity of a measured state to some target state phi. So my measured state is rho. I have a target perfectly entangled state phi, right? And I can use sort of diagonal measurements. This is measuring the two photons I in two bases m and n, right? And I can use these measurements to basically lower bound the fidelity of this state. And so we use this procedure to essentially measure a very, at the time, a very high dimensional state 3 years ago now, where we showed that this 9-dimensional state, well, this 11-dimensional state was entangled in at least 9 dimensions of orbital angular momentum, right, with a fidelity of 76% or so. Now, we've recently extended this, this procedure, this witness we modified it a little bit by really looking into the details of what does the continuous state of entanglement in position momentum look like. And it's described by this function, which we call the joint transverse momentum amplitude. And you can find more details about this in our recent publication in the journal Quantum. It's a sort of newer journal, which is why I'm mentioning it explicitly. So one finds that, you know, when you look at the joint transverse momentum amplitude for two photons in one dimension, y, you can sort of decide how you want to discretize this function, and you can develop sort of pixel masks that work for you, so that will maximize the entanglement and allow you to approach a maximally entangled state. Excuse me. Right. So using this concept of pixel entanglement, right? We recently showed that you can have very high quality entanglement. So we demonstrated 18-dimensional entanglement in this pixel degree of freedom. We've gone up to 55-dim entanglement, and we did it very quickly, like 3 minutes for this 18-dim state, which would usually take us days, right? So that 9-dim result I showed you took me 24 hours to measure before. And the many reasons why this works well, better, and you can find those in this paper. Right. So I'm moving ahead in the interest of time. So the last part of my talk is about taking this property of entanglement and now trying to transport it through something that would mess it up, right? Which is a complex medium. So we're all familiar with complex scattering media, right? They're everywhere. The wall in front of me scatters light. Your teeth, your skin is a natural scatterer of light. Piece of sugar as well. And also multimode fiber can be considered to be a complex medium, not as complex, of course, as some of these other ones, but it does mix light and results in a speckle pattern, right, of light coming out. So this is a picture that I took in the lab of light coming out of my multimode fiber. Funnily enough, this is showing you speckle within speckle, because the specular reflections off of my metal plate were also creating speckle, right? So the bigger blobs are speckled due to the multimode fiber, and the fine grains are actually speckled from the reflection. So there was this very nice work a few years ago from Thomas Chismar's group in Dundee at the time in Scotland, very close by, where they undid the scrambling inside a multimode fiber for a classical information transfer, right? So this is you're seeing real data here of an image being sent through a 30-centimeter section of multimode fiber. And you can see that the image is retained, the quality is retained quite well. And the way they did this is they figured out how to measure. Now, this, of course, has been around since 2010, the technique of measuring the transmission matrix of a complex medium. The transmission matrix of any medium, for that matter, is a matrix that maps a set of input modes to a set of output modes. So for a lens, a transmission matrix is quite simple, right? But for a sugar cube, it can have millions and millions of elements, complex elements, mind you. And these are measured usually by taking a set of probe states, I, sending them through the medium, and then detecting a set of output states, J, and then calculating these complex coefficients T, Ij that map the set of input modes to the set of output modes. Right, so you would end up with a matrix that maps these two modes, and in general, this matrix is complex. So I'm only showing you some absolute value here. And then once you know the matrix, you can of course diagonalize it and essentially find a set of modes that would not be scrambled by the matrix, right? And this equates to calculating the inverse of this transmission matrix T inverse, which is not in general an easy thing to do, especially for noisy systems. Right, so let's change gears a little bit and go back to quantum mechanics for a second. In quantum mechanics, we have this thing called channel state duality. And so if you imagine a scenario where you have this maximally entangled state that I talked about in the first part of my talk, right? And you put transmission complex medium with transmission matrix T in one of the photon arms, one of the arms of this state, the resulting state rho looks like this, right? And essentially what this channel state duality says is that statements about the state rho can be mapped onto statements about the channel. So this is a very interesting thing. It basically says that the state and the channel are one of the same things in quantum mechanics. If you have a perfect state, and if you have some complex scattering channel or any channel, you send part of the state through the channel, the state and the channel are one and the same things. So the entire channel is mapped onto the state, right? So the state kind of takes a photograph, let's say, of this channel. And this is called the Choi-Jamelkowski isomorphism, which can be credited back to some mathematicians actually back in the 70s. So what does this mean for our experiment? So I showed you how you can use a set of input states to measure a medium, one probe state at a time, right? But now using this isomorphism, basically what one can do is take one entangled state, send one particle of the entangled state through a complex medium, and lo and behold, the resulting state should then actually have all the information about the transmission matrix. So the state that goes through the transmission, so through the complex medium, phi t, then encodes the information of t ji in itself, right? So here, identity tensor t means identity works on one particle, which does nothing, and the t operates on the other particle, which essentially rotates this state in some high dimensional Hilbert space. So to undo the effects of scrambling, scattering, you can simply put an inverse operator in the path, right, that the photon went through, which would be quite similar to the standard classical way of doing this. However, in quantum mechanics, there's something very interesting. High dimensionally, maximally entangled states have this property where operations on either of the particles can be written or rewritten as operations on only one of the two particles, using sort of transposes and conjugates, etc. And so what we can do here is that we can unscramble the effects of this complex medium by only operating on the entangled partner. So we don't touch the medium, we don't touch the photon, we simply rotate the basis in which we measure the partner, and we should regain entanglement. Okay, so this is theory still. So now going to the experiment, let's start with an initially a very nice pixel entangled state in 7 dimensions. So here I'm showing you 2 mutually unbiased bases, right? So this is the pixel basis, this is a pixel mub, and we measure a fidelity of about 94% or greater. Now, if we send one photon from the state through a multimode fiber, we get no correlations, right? So here I'm showing you nice correlations. After the multimode fiber, those correlations go away. And usually at this point, we'd be disappointed. But now we realize that because of this Choi-Jamelkowski isomorphism, these scrambled correlation matrices actually contain information about the transmission matrix of the fiber, right? That's pretty cool. The noisy data that you would usually throw away is actually a photograph of the medium, that, except it doesn't have the phase information. It's just the absolute value of the transmission matrix. So then,
sorry,
yes,
we just have 1 or 2 minutes.
okay,
So
yeah, I'm close to wrapping up.
Great, thanks.
So I will kind of skip through this last bit where we employ the classical methods of phase stepping. We use a co-propagating reference to kind of measure the complex elements of this transmission matrix, right? And this is very similar to the way the techniques they use in classically. But just in the interest of time, I will skip ahead. And so we end up with a complex transmission matrix, right? Which we can then apply on the photon that didn't go through the fiber to rotate the basis and measure in a different basis on Alice, while on Bob we essentially measure the same thing as before. And we find that doing this, we can regain the correlations in this basis. So we basically regain our quantum correlations by simply changing the way, or by scrambling the photon that does not go through the fiber in a clever way. So now, of course, to certify entanglement, we have to measure in mutually unbiased bases, as I showed you before. And this involves some rotations of the transmission matrix. But we are able to, again, measure in all 8 mutually unbiased bases of this 7-dimensional state, right? Which then allows us to calculate a fidelity of at least 84% to a maximally entangled state of pixel entanglement. Right, so to summarize, I showed you how we can certify high-dimensional entanglement using 2 bases at least, right? Then I showed you how we generated and certified pixel entanglement in pretty high dimensions. And then finally, I showed you how we unscrambled this pixel entanglement through a complex medium. And interestingly, the entanglement was recovered by only manipulating the photon that did not enter the medium. So thank you for your attention. I just want to point out the 2 of the people who were very important to this work was my student Natalia, who's my first PhD student, and Hugo, as I already mentioned. And a lot of the pixel entanglement work was done in collaboration with my theory colleagues in Austria and the Czech Republic. Thank you very much.
Thank you, Professor Malik, for a really beautiful talk. We have time for 1 or 2 questions. So please, if anyone wants to ask, can raise hand.
Yaron, can I have a quick one? Sushil here.
Sure.
So thanks, Mehul. This is a fantastic presentation. If I don't say I understand you perfectly well, but if I do, then the unscrambling of the entanglement required you to do some process on the other photon, which was not going through the fiber, correct? Mm-hmm. So whatever process you did on that photon, is that process itself correlated with the fiber?
Yes, so that's a very good question. So what we do to the other photon is actually perfectly it's informed by the measurement of the fiber. So we measure the transmission matrix of the fiber by basically measuring the state. And then what we do on the other photon is we simply measure it in a different basis that corresponds to what the fiber does to its partner. So what I'm trying to say is that the entanglement doesn't actually go away. It gets rotated in a way that corresponds to what the scattering process in the fiber. And we can bring those correlations back by also scrambling up the partner in the same way or conjugate way as the fiber does its entangled partner.
Right. So the sub question behind that was that process that you did to the other photon, can that be considered some kind of a proxy to the multimode fiber now for future experiments?
Yes. And what's crucial is that it's that we are assuming that the fiber is pretty unitary in this case.
Okay.
Right. So we are able to kind of like bring back So it's a proxy in the sense that we're not losing information. We're just doing basis rotation.
Yeah. Okay.
So we assume that the fiber is simply rotating the basis around.
Okay.
But we've done some work actually building on this in recent months, where we don't necessarily need the fiber to be unitary, and there can be dispersion and all sorts of things as well.
Thank you so much. Thank you.
Yeah, thank you. I have actually a quick follow-up question on Sushil's question. So, if I understand right, the SLM it's a single SLM on a single plane that usually allows generating diagonal matrices, and the fiber in general can generate more complex. So, is it just for weak coupling that it works,
No. It's a very good point actually that you raised, and you're absolutely right. So by diagonal matrices, you mean the fiber only, sorry, the SLM does phase only transformations, right?
But even if phase and amplitude, it can only, if I write the transmission matrix of an SLM in the pixel basis, it's a diagonal because each pixel affects it.
Okay, right. Okay, I think I understand. So
Okay.
you're right. The SLM only does diagonal measurements even if they're phase and amplitude. But what we are doing with the SLM is not replicating the coupling, right? So the crucial point here is that the SLM allows us to change to any basis, any arbitrary basis. And you're right, the fiber does a complete mixing that is not replicable by one SLM, absolutely. But what we assume is that the mixing taking place in the fiber is a unitary rotation, right? Which it's pretty close to that in a short fiber. And so with the SLM, we can measure any basis, which then basically, so it's not actually, so go back to Sushil's point, it's not a proxy, but it's very unique to the fact that our fiber is a unitary rotation in this space. So, but yeah, let me think more about this. This is a very good point, and then actually relevant to what we are doing right now as well. So thank you.
Okay, thank you. So thank you very much, Raul, again for a great talk. And if there's no more questions, I think we can move on to the next talk of the session. So now we will have 3 contributed talks, 10 minutes each. And the first speaker will be Satadriya Singh, and he'll be talking about influence of phonon scattering in enhancement of thermoelectric power in composite silicon tantalum nanomaterials. So please, Satadriya, the floor is yours.
Okay. I am audible, sir?
Yes, you can.
Okay. A very good operative evening to everyone presented here. This is Satyendra Singh, UGC DS CSR Indore in low temperature laboratory, presented a topic on the untitled influence of phonon scattering in enhancement of thermoelectric power in composite SNT and T nanomaterials. So this talk is carried out under the outlines introduction and sample introduction. Sample has properties, topology, crystalline insulator, thermoelectric power, result, discussions, conclusion, acknowledgement, and references. So topology is a term, generally a mathematical term which deals some under invariance conditions, like some deformations under invariant conditions, like in mathematical, which has invariant conditions like genus, which has protected by Gauss invariant theorem. In condensed matter physics, topology deals with topological insulator and crystalline insulator. Topological insulator, which has non-trivial symmetry, protected topological order, which has protected by time reversal symmetry instead of crystalline symmetry. So this is the topological crystalline insulator as states here. The interior part of the system is insulating due to the Lorentzian force because the perpendicular interior plate present predominantly in these systems. So this part, interior part, bulk part is not contributing in the conduction. So only the surface part is contributing in the conduction. So the edge states only the contributing conduction. The spin momentum polite here. So the polite spin momentum which is logged. So this is the counterclockwise spin. This is the anti-counterclockwise spin. As a spin change the rotation, this also change the direction of the momentum. So if we operate the time reversal symmetry, also the mirror symmetry, because in crystalline insulators, mirror symmetry plays a vital role in these systems. So this is the 110 surface state in SNT present predominantly and all the other surface states 100 and 111 is also here. But in all the surfaces, this is topological crystalline insulator predominantly in the system. This is the billion zone counterpart here, and this is the gamma point at here. And this 110 surface, the if k points change the direction of the momentum predominantly in the these systems, then the Hamiltonian, if we operate the mirror symmetry on this Hamiltonian on the system, then this Hamiltonian preserves with the mirror symmetry. So this overall commutes with the system which has been shown here. The mirror symmetry operates on these eigenstates. Then this system change, there is no change in the energy. So Hamiltonian commutes with the total energy. And in this a PVT system and a SNT systems, PVT system not shows the crystalline insulator because there is no change in the continuous deformation of the bands. But if we see the SNT, here are two aspects. The we are looking on this, we are see the two aspects here in SNT. This is the band diagram of the SNT. This is the red color which is shown on the conduction band, and this is the balance band. But as the change here or the continuous deformation, this is the change occurs. Balance band change into conduction band, and conduction band change to the balance band due to the spin polarized states in these systems. Thermocouple measurements also here. This is the Peltier element which has been shown here. This is the semiconductors PN semiconductors. Electrically, these are in series, but thermally in parallel. Why these are electrically in series? Because if we connect in electrical, the electron faces the resistance, due to which Joule heating effect, a heating is produced here. So there is a change between the cold and hot side if we connected between here. So there is the carrier density difference between N and P types. So due to the difference between the chemical potentials here, a current flows in the circuit because there is a temperature difference is here. So as the temperature gradient is there, a voltage gradient is developed here. And the ratio of the voltage gradient with respect to temperature gradient is known as the thermopower, and vice versa is known as the Peltier effect. We do applications thermoelectric in energy applications because the energy harvesting and the wastage energy we can reuse in the form of the electrical energy. These are the automobiles and several applications here. But in this part is the hot zone, as where the engine is the car there, and a peltier in a connected between here. So the temperature gradient between can in the form of the electrical energy restores here, and this restores electrical energy we can reuse in the form of the lightning of the car and mobile charging etc. And these are also the applications here. And this system is very important due to the respects of the thermoelectric properties as well as the topological crystalline insulator properties. Due to the enhancement of the thermopower, these are the various samples which has been shown here. The literature report is here. The thermopower enhances as the temperature increases. This is also reported in the high temperature region. And SNT is also available in P type as well as the N type. And room temperature thermoelectric reported 0.3 at room temperature, but the best thermoelectric material SNT as 9 to 3 Kelvin with carrier concentration 10 to the power 18 per centimeter cube. We have used lab facility during the synthesis of the sample and several measurements performing during the measurements to consider the effect of the pollen influence mechanism. So we have used the precursors pentanediol and SnCl2 with respect to in heated with microwave oven, and these samples heated and so tellurium has also heated in TOP, and we are changing the protocol of the time of the 4 samples. We are changing the vacancies of the tellurium growth. So there is the enhancement in the tellurium occupancies as well as the temperature is predominantly protocol in the system. We have carried out the thermopower measurements by differential scanning sensor homemade system in our lab, and this is the commercial PPMS systems. Why these systems are composite materials are interesting for thermoelectric performance? Because there is the high and low mobility electrons scatters from the carrier centers, due to which there is a reduce in the thermal conductivity, but there is no much more change in the electrical conductivity. So due to the cumulative effect of the electrical conductivity as well as the reduced thermal conductivity, there is the enhancement in the thermopower. So there is the bulk reported on SNT and T materials which state the phonon scattering mechanism predominantly present in the system. So these are the variations of the XRD and SNT measurement to confirm the phase formation of the SNT and its nanocomposites. These blue triangles indicate the SNT peaks, and in its nanocomposites, this is the tellurium peaks is predominantly present as well as the SNT peaks. We have retrieval refinement to confirm the phase formation. So we have a double refinement, double phase, as well as the SNT and the tellurium. So we have calculated cell parameters of tellurium and TE. And with the occupancy variation of the SNT system as well as the tellurium systems, we changing the protocol of the time. So there is the changing in the tellurium phase. So there is the occupancy changing, and in ST2 system, there is the enhancement of the occupancies with the temperature protocol of the system. So also this change reflects in the morphology measurements. This is the SNT system, which shows the hexagonal phase of the morphology, and this is the growth of the nanorods, which is enhanced as well as the temperature is increasing is there. So there is the enhancement in the growth of the nanorods, and the SNT seeds is predominantly present in the system is also here. So there is the enhancement in the growth of the nanorods. So this reflects enhancement of the thermal power also. So this is the EDX measurements spectrum of the. So this shows the growth of the tellurium nanorods in the axis. These are elemental mapping of EDX measurements and its nanocomposites. So this shows the stoichiometric ratio of SNT is nearly 1:1, and this is the elemental of mapping of SN, T, and T. So the cumulative change of the tellurium and SN is predominantly seen here. So this NN shows that there is the predominantly TE present in the system is here. We have also to further confirm this, we have also take the optical image of the SNT system and as well as the nanocomposites, which also state the change in the morphology and predominantly enhancing the growth of the nanorods. So for the confirmation of the phonon influence mechanism in these systems, we have calculated the heat capacity measurements, which is have been fitted by this equation, and the coefficient of the gamma Sommerfeld electronic coefficients also state that, which had also plotted this graph Cp by T as the function of the T square. This state the electronic configuration part is the very weak, and theta D indicates that there is the vibration, phonon vibration enhanced in this mechanism. We have calculated carrier concentration and heat capacity measurement with the cumulative effects of thermal power and carrier concentrations with heat capacity. So we have seen there 10 to the power 18 per centimeter cube, which is predominantly axis in this system. We have also calculated MR measurements. Okay,
sir,
sir.
Can you just try to wrap up, because we are almost out of time.
Okay, sir. We have also calculated the MR measurements, and we have fitted with this model. And this model states that there is also the carrier concentration fitted with this model and calculated here, and carrier concentration as the function of the by this relation we have calculated from here, and fitted this resistivity as the function of the temperature. There is the enhancement in the phonon mechanism, which has been shown here. There is the enhancement in the Einstein temperature, which states that the phonon scattering mechanism is enhanced, and this also states that the power law variation, the predominantly phonon scattering mechanism also present in this as the variation of the protocol of the temperature. The phonon influence mechanism enhanced in the systems, and we have further confirmed this phonon scattering mechanism in thermopower. This is the parent black graph of the SNT sample, and the variation with temperature, the phonon scattering mechanism enhanced. And this single line fitting states that on the high temperature regime as well as this temperature regime, this states the phonon influence mechanism is enhancing, and we calculated Fermi energy with this variation. So the Fermi energy is decreasing, so S increasing, because in inverse relation is also here. We have calculated the effective mass variation.
Sorry, sir.
Yeah, I think you can. Yeah.
Can you please move on to the conclusions and main findings, because we're really over the time?
Okay.
Thank you.
We have conclusion here. We have synthesized this sample and by microwave synthesis and its nanocomposite also. And for the confirmation of phase, we have XRD and retrieval refinement measurements. Elemental mapping states that SNT phase increasing as the growth of the tellurium rods. Both SNT and its P-type enhances. Thermopower is also enhancing as the predominantly tellurium is axis. So there is the enhancement in the thermopower. Significant NS in the linearity of S and comparison of thermal conductivity measurements from literature indicate the phonoscattering mechanism plays a vital role in enhancing of TEP. These are references, acknowledgements, and thank you.
Thank you, Sundar. So we are really over time. So unless there's a super quick question for anyone, then we should probably move on to the next speaker. So thank you. Yeah. And our next speaker.
Yeah, can you please stop sharing the screen? Yeah, thank you.
Our next speaker is P.A. Saha, and he'll be talking about high refractive index dielectric rings in liquid crystals and tunable metasurfaces. And I remind the speakers there's 8 minutes and then 2 minutes. Please leave 2 minutes for discussion. So is our speaker here?
P.A. Sahare, are you present, please? P.A. Sahare?
Yes, sir.
Yeah. Can you share your screen and start your
Yes,
presentation?
sir. Are you able to see my screen, sir?
Yes.
Okay, good evening, sir. My name is Pratiksha Ashok Sakre and I am from Mahindra University, Hyderabad. I would like to give a presentation on high refractive index dielectric rings in liquid crystal as a tunable metasurfaces. So these are the outlines of my presentation, like introduction, motivation behind structure designing, simulation, work done so far, conclusions and future work. So what are metamaterials? Metamaterials are the artificial structures having lattice constant is very less than incident wavelength of light. So having properties beyond the conventional materials, and it is known that the metallic structures at subwavelength dimension gives rise to interesting electromagnetic properties like negative permeability, negative refractive index, and optical chirality also. So here we use dielectric structures because of these structures support the magnetic resonances and overcome losses due to heat dissipations. And we specially use here liquid crystal as a dielectric medium. So these are highly birefringent, anisotropic, and non-linear fast response to external stimuli like temperature and electric field. So this is the designing and rings in electromagnetic simulation. We perform 3D simulations by using CST Microwave Studio. Here the collective photonic response of the high dielectric index structures is determined by using numerical modeling, which is based on solving numerical Maxwell equations with finite element method. So in circular and square rings, these are placed in XY plane, which are filled with the air and liquid crystal medium. So here we used periodic boundary conditions which are applied in XY directions, and electromagnetic wave is incident on Z axis with polarization along Y direction, and magnetic field is along X direction. These are parameters we used for designing structures. Here we vary the thickness and orientation of liquid crystal molecules at constant periodicity of 2.5 micrometer. So we carried out simulations here in air medium with comparatively study with tellurium and gallium arsenide. So we to look the effect of refractive index resonance characteristic. So electromagnetic wave is this electromagnetic wave in frequency range 1 to 100 terahertz incident in on the rings. So electromagnetic and here we observed the resonance frequency of gallium arsenide shifted towards the lower frequencies. So below terahertz, here the incident light undergoes the Fabry-Perot oscillations, and while above 80 terahertz, it shows the higher order modes. So in between these two regions and the wavelength of incident, we observe the scattering from the dielectric mediums. So circular rings shows the resonance characteristic at 82.66 terahertz, which is here electric dipole is present, and 92.2 here this electric hexapole. So same as in square rings also exhibit higher order modes like electric quadrupole, hexapole, octopole, and decapole also. Here we studied the circular effect of thickness. So here the resonance, as observed in previous slide, in very thick rings only they support only electric modes, and the magnetic modes are comparatively absent. But we increase the thickness here 0.2 to 3 micrometer. Then there is some magnetic modes are present. So as like circular rings here, as like square rings, as like circular rings here also, in square rings we similar type of characteristics we have observed, but here when we increase the thickness, these electric modes are not support, but when we increase the thickness, the magnetic dipole modes are support. So here we used a liquid crystal as a medium. So this one is an anisotropic medium. Here we studied the scattering parameters as a function of angle. We rotate the liquid crystal angle angles at 0, 30, 45, 60 and 90 degree with x, y, x, z and y, z planes. So and these are the input parameters in the CST softwares. So and check the response of tellurium structures in different orientations of liquid mediums. So just changing liquid crystal angles, here we found out like comparatively some angle some modes are like displace or enhance these resonance modes. So this is one characteristic which we observe here. So here we observe some modes like electric dipole, octopole, quadrupole modes in like air as well as square rings in liquid crystal mediums. So to obtain the details of these magnetic and electric modes at excited resonance, we need to do some work in detail. So this is our future work. So conclusion of my presentation is we studied the effect of geometry and refractive index of dielectric rings, which play a significant role in resonance characteristic. Squaring shows the sharper resonance characteristic and high field localization. Thinner rings support the electric mode, while rings of thickness most exhibit spectra. Resonance spectra of high refractive index dielectric rings, circular and square, made up of tellurium liquid crystal, are studied using finite element method. So in liquid crystal medium, the response band become asymmetric, and here also we observed some higher order modes. So our future work is detailed multiple analysis and experimental confirmation of these results. So thank you.
Thank you very much, Ms. Sarah, for a nice talk and for keeping the time. Do we have any questions, Ms. Sarwar?
Can I go again, Yaron, once, quick one?
Sure, go ahead. Steve.
So yeah, Ms. Pratiksha, I missed the point. Why is tellurium of interest?
Because sir, it have high refractive index.
Okay, so the refractive index is
Yes.
material.
Sir, matter. Refractive index matter.
Okay.
So it has 5.7 refractive index.
At what frequency is this?
We used here 1 to 100 terahertz frequency.
5.7. Okay. And do you know if it's a machinable material? Is it easily machinable?
No, sir, no idea.
I see. Okay, no problem. Thank you.
Okay, sir, thank you. Should I stop my screen?
Yes, stop
Yes,
sharing the
please.
screen.
Okay, thank you.
So thank you very much again, Ms. Sarwar. And the last talk for this session is Muhul Chandra Paul, and he'll be talking about fabrication of silver nanoparticle doped phosphorite glass-based optical fiber and thermally induced tuning of its spectral properties. So please, Mr. Paul, if you can share your screen.
Yes, good evening. Can I share my slide?
Yes, please share. Yes.
It is visible?
Yes.
Yes.
Okay. So good evening to everybody. Actually, my topic is fabrication of silver nanoparticle doped phosphosilicate glass-based optical fiber and thermally induced tuning of its spectroscopic property. Basically, outline is objective, problem definition, reason for selection of this kind of glass, importance of silver nanoparticle in silicate glass, fabrication methodology, study of nanostructuration, study of optical absorption fluorescence property, study of tuning absorption and fluorescence property under heat treatment, and future study and conclusion. Basically, objective is development of silver nanoparticle doped optical fiber by MCBD solution doping technique and tailoring of the composition of this glass so that silver nanoparticle sustain the particle size within 5 to 10 nanometer so that the loss of the fiber become very low, and the tuning of this thermal property, spectroscopic property with increasing the temperature gives rise to rest shifted of the optical absorption and fluorescence characteristics that can be useful for its temperature sensing and bioimaging probing. The problem is that silver nanoparticle is very difficult to job for uniform distribution within the core of the optical fiber, and size should be maintained uniform. If it is greater than 10 nanometer, loss of the fiber will be high. Another is silver easily vaporized during high temperature melting point for making of the fiber. So this kind of precaution can be taken out. Why it is? Because it is silver oxide is a very low solubility silver in a silica glass, and incorporation of aluminum phosphor increase the solubility, and incorporation of aluminum phosphor gives rise to non-bridging oxygen, which increase the reduction of silver ion to precipitate the silver metal into the basically silicate glass. And during sintering process, the silver oxide also decompose and form metallic silver and oxygen. This is the actual procedure. Silver form silver phosphate, then it is decompose silver into phosphorus pentoxide. Important is that metal nanoparticle of optical fiber in different glass, not only germanium silicate glass also gives rise to highly nonlinear optical property and which show strong nonlinear refractive index and also surface plasmon resonance. And basically, the purpose is that using this kind of fiber to make a broadband supercontinuum visible store under suitable pumping scheme, and also the fiber show low energy threshold. This is the basically theme fabrication of fiber, MCBT solution doping family, drawing of fiber, then study of metal nano characterization, tame absorption study, electron proof microanalysis study to basically distribution of silver nanoparticle along the diameter of fiber, and study of the absorption fluorescence spectra under pumping and 406 nanometer pump source, and study of the tuning property of the absorption fluorescence under heat treatment. We basically deposit a phosphosilica layer, deposition temperature 1475 to 1500. Then we soak the layer silver nitrate, also aluminum nitrate, soaking pure 45 to 60 minutes. Then dehydration followed by helium. Then during precipitation, it gives rise to sintering process, and high temperature it gives rise to silver and nitrogen oxygen. And we maintain helium this environment. Then we make a PFOM. PFOM is a solid rod which is around 10 millimeter diameter. Within the 10 millimeter diameter, pore diameter is around 0.1 millimeter, where silver nanoparticle is doped. From this PFOM, we dot a fiber. This is the MCB, the first porous layer. Then soak this layer. Then after soaking, goes to oxidation dehydration process, and then gives rise to sintering, collapsing, and finally we enter PFOM. This is the tool we have used: material optical characterization, EPMA, high resolution TEM, basically spectrophotometer, optical spectra, fluorescence spectra for Jokakoa with heating, all kind of this one. This is the basically fiber PFOM make, where this is the core region where silver nanoparticle dope is fabricated, and this is a silver fiber dyeing. This is the microscopic view of the fiber. This is the distribution of silver along the diameter of the fiber. This is the distribution of aluminum phosphorus, aluminum along the diameter of the fiber. This is a basically EPM analysis. This is the refractive index profile of the fiber. What is the refractive index of the core and cladding layer? From this, core diameter is 12.5 micron and Na around 0.2 micron. And this is the absorption property which we have measured basically under room temperature. After that, we increase the temperature 250 to 650 degrees centigrade, and absorption field gradually increase and shifted to a higher wavelength size. This is basically with increasing temperature, size of the silver nanoparticle increase from most probably silver nano cluster. And we have done this. This is basically also after heating, and then we cool. The same spectra occur, no any change. So this can be reversible process occur. This is the TEM analysis, 250, basically 450, and then a 650, and gradually the size of the nanoparticle gradually increase. And 350, 650 we have taken high resolution spectrum, and some crystalline nature plane occur. This is a metallic nanoparticle developed under heating 350, 650 degrees centigrade. And this is the fluorescence spectra we have taken with increasing the temperature from 250 to 500, gradually rate shifted of the peak, and the shifting is wavelength is around 17 nanometer. This kind of phenomena will be useful for temperature sensing and bioimaging fiber. This is the beauty of this nanoparticle of fiber we have developed in our lab, basically phosphosilicate glass. So future plan of work is that we have planned to incorporate heavy metal, basically lead and bismuth, into the core of the glass, so that it increase the percentage of the silver nanoparticle for enhancement of the further basically fluorescence peak, and study of the plasmonic property of the silver nanoparticle of optical fiber to surface and Raman spectroscopy with metal enhanced fluorescence for making of optical plasmonic resonance, and study also supercontinuum source under suitable pumping scheme. Conclusion that silver nanoparticle dope fiber, we have made phosphosilicate glass by MCBD modified chemical vapor deposition followed by solution doping technique. We have maintained uniform silver nanoparticle 5 to 8 nanometer along the whole diameter of the core. The presence of silver nanoparticle in the dawn fiber is confirmed from EDX, and also an absorption spectra will give rise to absorption plasma resonance absorption peak 405 nanometer. This silver nanoparticle show for broadband fluorescence starting from 500 to 800 nanometer after excitation within its resonant band using 405 nanometer band. And Stokes strip of the fluorescence peak occur in visible after heating 250 to 500 degrees centigrade when is from 405 nanometer. Such kind of phenomena will be useful for temperature sensing and on the bioimaging purpose. So acknowledgement is the CIO, Mexico, this is our partner, Department of Science and Technology, Council of Scientific Industry Research, Corning Incorporate. This is industry also involved in this, Advanced Material Characterization Unit, CGCRI, and all staff member of the FOBD. Thank you very much for your kind attention.
Thank you very much. So Session is now open for questions. Maybe I'll start with a quick question. So relating to Mahu's earlier talk about interesting complex dynamics in multimode fiber, can you make these fibers with a larger core so they will guide multiple transverse modes? So you showed a core of 12 microns. How big can the core be? How large can it be?
Actually, we can go up to 50 micron with respect to 125 micron of the cladding diameter.
And how long is it practical?
Practically, that will depend on the length of the preform. Basically, if the preform solid rod is around 10 millimeter diameter and 50 centimeter length, then from that whole preform we can do around more than 4 kilometer fiber continuously with online resin coating.
Thank you. Are there more questions to the speaker? If not, then I think it's a good point to thank all the speakers of this session for really excellent talks, and thank you all for participating. And I hope to see you in the following sessions.
Thank you very much, Professor Mumberg. So thank you. I thank all the speakers, invited speakers, and all the contributor speakers for a wonderful session. And I particularly thank Professor Bungman for sharing the sessions. Thank you very much.